This is Akhtar Munir, and I am going to present my recently published work in CVPR titled Bridging Precision and Confidence: A Train Time Loss for Calibrating Object Detection. My co-authors are Haris Khan, Salman Khan, and Fahad Khan. One of the major issues in deep neural networks is that they are often miscalibrated. Almost all work towards improving model calibration targets the task of classification. However, the calibration of object detection models has not been actively explored. Similar to classification models, object detection models also occupy an important position in many safety-critical applications. Uncalibrated DNN-based detectors output less trustable predictions as the probabilities of inaccurate predictions are relatively high. We study the calibration of object detection models for both in-domain and out-domain predictions, and observe that the recent state-of-the-art object detectors are rather miscalibrated when compared to their predictive accuracy. We propose a novel train time auxiliary loss formulation, which explicitly attempts to bridge the model's precision with the predicted class confidence. It leverages the count of true positives and false positives in a mini-batch, which are then employed to construct a penalty for miscalibrated predictions. Our loss function is designed to be used with other application-specific loss functions, and our goal is that the detector predicts well-calibrated probabilities for accurate predictions while lowering the probabilities of inaccurate predictions. There is little to no progress in studying the calibration of DNN-based object detection models. These models are central to many vision-based safety-critical applications. The majority of efforts tackling model calibration focus on calibrating in-domain predictions. A deployed deep learning model can encounter samples from a distribution that is radically different from the training distribution. Therefore, a real-world model should be well calibrated for both in-domain and out-domain predictions. There are two methods for model calibration. Post-processing. Very limited parameters are available to tune for estimation of calibration measure. It requires a holdout validation set for that purpose. It may not be optimal for dense prediction tasks. Train time loss. No holdout validation dataset is required. Architecture is trainable and huge trainable parameters are available. Classification-based calibration losses are suboptimal for the detector's calibration. A novel auxiliary loss formulation that explicitly aims to align the class confidence of bounding boxes with the accurateness of predictions. Since the original formulation of our loss depends on the counts of true positives and false positives in a mini batch, we develop a differentiable proxy of our loss that can be used during training with other application-specific loss functions. There is a lack of direct supervision for the model to promote higher confidence for accurate predictions and lower confidence for inaccurate predictions. Motivated by this observation, we leverage the statistics associated with high scoring and low scoring box predictions to calibrate the detection model. We utilize the true positives and false positives to span the precision and confidence space in order to maximize the probability scores for accurate predictions and minimize the same for inaccurate predictions. Specifically, we discretize the confidence and the precision space into four partitions for categorizing the accurate and inaccurate detections. Finally, we formulate the differentiable surrogate approximation to our auxiliary loss function. Now we move towards the experiments. Our baseline for detection models are transformer-based deformable detector and CNN-based one-stage object detector FCOS. We have done extensive experiments on various benchmark datasets, including in-domain and out-domain scenarios. With our BPC loss, we observe improvement in the calibration of object detector. Calibration performance is shown on MS COCO and Cityscapes for both in-domain and out-domain scenarios. calibration performance along with the detection performance while showing the model agnostic capabilities of our proposed VPC loss. We are able to improve in calibration performance with no significant drop in the detection performance. On more image corruption benchmark datasets, it is shown that the proposed loss function improves the calibration performance in the challenging outdomain scenarios. We show further qualitative results that our loss function makes the detector predict well-calibrated probabilities for accurate predictions while lowering the probabilities of inaccurate predictions. Thank you very much for listening to the talk. For more details, please visit our poster and the given link.